Okay, so let us begin. So we were talking about semantic notions. And we said that semantic notions are what have to do with the meaning of our formulas. The meaning of our formulas is the way they compute true, false values. So the first one that we saw is the notion of alpha is satisfiable. And that means there exists some truth assignment V such that V of alpha, V hat of alpha equals true. And the second one was alpha is a tautology. And it meant that for every truth assignment V hat of alpha is true. And we saw some examples of tautologies. We said that in general, the checking whether a formula is satisfiable or tautology is difficult. It may take an exponential number of steps because we need to write the whole table. But if the formula is made of with a lot of errors, then sometimes we can do it more cheaply. So let's look at another example. And let us look at the formula P arrows. Or let me, P and Q maybe to, let me use A arrows, B arrows C, arrows A arrows B, arrows A arrows C. So if we look at this formula, so what it says basically is that if A implies that B implies C, then if A implies B, A implies C. So how do we check if this is a tautology? So since it is made mainly of the arrow connective, we know that the only way, we want to check if something is a tautology, we search for the main connective. We find the main connective by counting paratheses. We ignore the first one. Then we look for the first place of equality. So here I have +1, +2, +1, 0. So this is the first place where the number of left brackets equals the number of right brackets when I ignore the leftmost. So this means that this is my main connective. So my formula is made of two subformulas, this one and this one. And now, if the main connective is arrow, the only case that this will be false would be the case where this is true and this is false. So if I want to check if this can be false, the only option is that could this be true and this be false? Right? And then I look at this formula. And again, I delete the parentheses at the end. I count +1, 0. This is the main connective here. So the only way, so this is again, the main connective is arrow. And the only one, so I have here, this guy implies this guy. And the only way this could be false is that if this guy could be true and this guy would be false. And again, the main connective here is an arrow. So the only way that this would happen is if A was true and C was false. Right? And then we can trace it back. So A was true, and we want this to be true. So if this is the case, then B should have been true. But now we know that A should be true, and B should be true, and C should be false, because this is what we concluded here. But in that case, this formula, B true arrows false is false, and true arrows false is false, so this cannot be true. So we ruled out the possibility that this formula will be false, so we know it's a tautology. We know it's always true. Okay? But of course, if you don't like this kind of argument, you can always draw the full truth table. The full truth table, we have 3 variables. We'll have 8 rows in it. Okay, so these are tautologies. And we can already see that there is a relationship between being satisfiable and being a tautology. Those notions are closely related. So here is a very simple claim. Alpha is a tautology if and only if the negation of alpha is not satisfiable. So we have a relationship between being a tautology and being satisfiable. And I will not even write down the proof. I will just explain it in words because it is so kind of immediately follows from our definitions. Because alpha is a tautology means that under every truth assignment, alpha will be true. Which means that under every truth assignment, the negation of alpha will be false. Which means that under no assignment, this will be true, so this is not satisfiable. And vice versa. Okay? And we can add another notion here, which is also closely related. We say that alpha is a propositional contradiction if, so this is another definition, if for every truth assignment V hat of alpha is false. So we call it a contradiction if it is always false. And again, anybody sees an immediate connection between any of the 3 notions that involves the third notion?
Tautology is the opposite.
So what do you mean is the opposite?
Negation.
Okay, so can I say that every tautology is a negation of a... So here is a question to you. Is it true, I mean, you can see from my tone what is the answer. Is it true, is it the case that every tautology alpha is of the form neg beta for some contradiction beta? Right? I mean, the natural thing to think is, oh, tautologies are the negations of contradictions. Or is it true that every contradiction is the negation of a tautology. So can you give me an example of a tautology that is not of this form and of a contradiction that is not a negation of a tautology? Right, so here is a good example, right? Look at this one. This is not a negation of a contradiction because this is not a negation of anything. And it's still a tautology, right? So let's try another thing. So this is the answer is no, and we have the example there. Is it true? Is it the case that every contradiction alpha is of the form neg beta for some tautology beta? Yes?
You can have A and not A.
Right. So the answer is again no. And an example here could be take alpha to be A and not A. Right? It is not of the form neg beta because it doesn't start with a negation. So what is true? So those two things are too strict to be true. But what can we say that is true about the connection between the relationship between tautology and contradiction? Yes?
For any contradiction alpha, then neg alpha will be a tautology, and vice versa.
Right. So we can say that, so it is true, let me just squeeze it here, that alpha is a tautology if and only if, so I'll write if with double F for if and only if, neg alpha is a contradiction. I mean, I cannot claim that if alpha is a tautology, then there is a neg inside it, but I can claim that if I add neg to it, I will get a contradiction. It's hard to read? Okay, so we have those simple notions that they are all related. They are all notions that talk about one formula. Are there any questions at this point? Okay, so let us now move on to notions that involve more than one formula. So these were semantic notions about a single, talking about single formulas, the single propositions. I want to talk about notions that involve more than one proposition. So another one, so our fourth semantic notion is, I will say that alpha logically implies beta, so this is a new notion, logically implies, if for every truth assignment V, if V hat of alpha is true, then also V hat of beta is true. So this talks about the relationship between two propositions. Alpha logically implies beta. If for every assignment that makes alpha true, it will also make beta true. So can you give me an example of such pair of formulas? Yes?
A and B and B and
A and B. So you claim that I'll take alpha to be A and B, and I'll take beta to be B and A. Right. So every truth assignment that will make this one true will have to give both alpha A and B the value true, and therefore it will make this one true. Yes? Right. Another one is let alpha be P, and let beta be not P. So those are examples of even something stronger, that each of them logically implies the other. So in such cases, we say that they are equivalent. So let's call it 5. We say that alpha and beta are logically equivalent if each of them logically implies the other. So here we had two examples of logically equivalent formulas. Each of them, if it's true, yes?
You use the similar sign for alpha and the equal sign for beta.
Oh, yeah, I should use the, it's a good point. I mean, I should use this one because, yeah, I mean, and later on it will become more confusing. Now we don't have equality in our language. So therefore, we cannot misinterpret the equality as something different. But later we'll have a language in which equality will be part of the symbols of the language. And then it will be very important to keep this in mind, to distinguish between a statement that we make about the formulas and something which is part of the formula. Right. Thank you. Yes?
Okay, so I'm not sure if we have our definition the way we want it, because our definition does not imply that if the alpha is false, then also the beta is false.
Okay, so let us really address this point. So first of all, let us look at some examples where I have logical equivalence, where I have logically implies but not logical equivalence. So can you give me an example of alpha that implies beta, but they're not equivalent? Yes?
Alpha is just A, beta is A or B.
Right. So I can take alpha to be A and beta to be A or B. Now I claim that alpha logically implies beta, but beta does not logically imply alpha, because we do have an assignment that makes this one true and this one false. That's the assignment that have false here and true here. Right? So we can have this thing. But now we can say a few things about the relationship between, so now we have 5 notions. We can play all kind of games with them. Some of the games I'll leave to the assignment. Some of the games I'll leave for the final exam. And some of them I'll do here. So here are some of the claims that we can say, that we can show. So here is a simple claim that alpha logically implies beta if and only if alpha arrow beta is a tautology. And why is that? First of all, if alpha, assume, I want to show you that alpha logically implies beta, then alpha arrows beta is a tautology. So assume, by way of contradiction, it's not a tautology. If it's not a tautology, you know what, maybe I'll write down the details, because it's not that it's so complicated, but it is important to me that you see how I reason about it, so you will know how to explain things fully in an assignment or an exam or something, okay? So this is kind of a demonstration of the amount of detail in the argument that I expect from you. So here is my proof of this claim. So I have here an if and only if. So when I have an if and only if, I need to show two directions. Right? So the first direction, assume alpha logically implies beta. Now we have to show that this is a tautology. So I can argue by way of contradiction. Assume, so now, by way of contradiction, if alpha eros beta is not a tautology, because I have to show that it is a tautology, so I assume it's not a tautology and get a contradiction. So assume it's not a tautology, then what does it mean? For some truth assignment V, V hat of alpha eros beta is what? Is false. But now we can go to the truth table of errors by the truth table of error. For that assignment, truth assignment V, we get V of alpha is true and V of beta is false. Because the only way that this will not be true is if the head is true and the tail is false. Now, what's wrong with that? It contradicts our assumption here. Contradicting our assumption, this assumption. If alpha logically implies beta, then for every V that makes alpha true, this V should also make beta true. So we showed one direction. Right? Now we have to show the other direction. So we assume that this is a tautology, and we can assume by way of contradiction that alpha does not logically imply beta, which means there is some V that makes alpha true and beta false, but under this V, what will be the value of alpha eros beta? False, because alpha is true and beta is false. Okay, so now we need to argue the other direction. Now we have to argue in this direction, and I leave it to you. Okay, so we see a connection between the notion of logical implication and the notion of a tautology. And we can see all kind of, going back to the question that I was asked 5 minutes ago, we can see all kind of other nice properties of logical implication. So for example, here is another claim. If alpha is a contradiction, then for every beta, alpha logically implies beta. So let us first prove it. It's not difficult, but then see that there is something unsettling about this statement. Basically, it says if you assume a contradiction, then you can prove everything. Right? Because if you start with a contradiction, it logically implies anything else. So why is this true? Because if alpha does not logically imply beta, there must be some v that makes alpha true and beta false. But no v will make alpha true. Right? So this holds this, the implication, the logical implication holds vacuously. In the sense, the logical implication means whenever alpha is true, beta should also be true, but alpha is never true. And we can even go on. I mean, it's okay. So what do we have so far? We have semantic notions that apply to single formulas, like being a tautology, being satisfiable, being a contradiction. And we had one notion that talks about pairs of formula. Alpha logically implies beta, or another notion that applies to pairs of formulas, which is alpha and beta are logically equivalent. Now I want to extend our discussion and talk about semantic notions that apply to sets of formulas. So we move forward and talk about semantic notions regarding sets of formulas, not even just two, or propositions. So let me use the notation, I'll use the notation sigma, denote a set of propositional formulas and my next notion is that I say that, so here is notion number 6, I think, sigma logically, or let me start with something even more basic. We say that sigma is consistent sigma is satisfiable, so it will be more similar to what we've already seen. Satisfiable if there exists some truth assignment V such that for every alpha in sigma, v hat of alpha equals true. So an example, I can give you an example of an infinite such set. So here is an example. Let sigma be the set P1, P2, P3, Pn, the set of all propositional variables. I claim that this infinite sigma is satisfiable. How can we show that this is satisfiable? All I need to show is give you a truth assignment that makes all of them true, right? So sigma is satisfiable. Sigma is satisfiable as demonstrated by the all T truth assignment. Yes.
But of course, this example is a little tricky. The same way that we won't like the example of A implies B and P implies Q. It's the same thing.
What do you mean? I don't.
I think that the elements of this set are just the same thing. I'm just saying I don't like this example.
What you said about this example? You don't like it?
Yeah, it's just, yeah.
Okay, you don't like it. Okay. So let's look at a different example. So let's call it sigma 1, and let's say sigma 2 is the set of all alpha I arrows alpha j such that I, and not alpha I, pi arrows pj such that I, j are natural numbers. Do you like this set better? No. Why not? So how do I show that this is satisfiable?
Basically, what I was thinking in my mind is that maybe we have an infinite set of formulas that are not logically equivalent, like you face your set. Your set, they are logically equivalent.
Those are not logically equivalent.
No, let's say
P is not logically, P1 is not logically equivalent to P2.
yeah, I'm confused.
I think he's thinking that they are similar in their syntax, that they're all similar variables.
Okay, so what about this one? How can we show that this is satisfiable? Can you give me a truth assignment that makes all of them true? Yes. All false, right. It's not just that the assignment all true will make all of them true, but also the assignment all false will make all of them true. So it's a little bit more interesting than this guy. There's more than one assignment that makes it true. Yes?
So so the assignment B has to be one assignment for all of the elements of sigma?
Right. One assignment for all of the elements of sigma. Right. So here we had only one satisfying assignment. Everything had to be true. Here we have two satisfying assignments. Either all is true or all is false. Let me show you an example in which we have infinitely many satisfying examples. So let us look at the sigma 3, which will be the set of all pi arrow pj such that I is less or equal j. What will happen now? Can you show me, first of all, can you show me one truth assignment that satisfies all of them? What? All true. So of course, V1, which is the all T, satisfies everybody here. Can you show me another one that satisfies all of them? Yes.
V1 is false for all ti where I is less than some number. And
Right.
for all else.
So let's have for every n, let Vn be as follows. Vn defined as follows. Vn of pi equals false if I is less or equal n, and true if I is more than n. So for each n, I defined an assignment Vn. And now I claim that each of the truth assignments Vn for every n satisfies sigma 3. Right? Because what will happen is at the beginning I'll have a bunch of, so I have here P1, P2, P3, Pn, Pn plus 1, Pn plus 2, and so on. Right? And now assume that I have something like false, 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 and then it becomes true. Right? So what happens if I take a pair, Pi arrows Pj? If Pi comes from here, then since the head of the implication is true, the implication will be true. If Pi comes from here, then it is true, but the Pj has a higher index, so Pj will also be true. So the implication will again be true. So this sigma has infinitely many different truth assignments that show that this is satisfiable. Okay? So we have a notion of an infinite, or not necessarily infinite, but it's a semantic notion about sets of formulas. This set of formulas is satisfiable. And we can combine those things. I say that, I mean, although all those notions look very simple, we start, things can become pretty interesting here. So, but let's go into what's going to be our seventh notion now. Number 7, let sigma be a set of formulas and alpha a formula. We say that sigma logically implies alpha, and we denote it by sigma, and I have this lying down on its side, pi alpha. That's a common notation. Sigma logically implies alpha. So I use this tilted pi, denoted by this if for every truth assignment V, if for all alpha in sigma V hat of alpha is true, then also V hat, oh, that's not good. So let's call for all beta, V hat of beta is true, then also V alpha is true. If all of them are true, then so let's go to examples. Maybe it will clarify it a little bit. So let us look at our simplest example. So here is an example. Let sigma 1 recall that our sigma 1 was the set of all pi such that I in n. Okay? So the set of all that was our sigma 1. And now I claim that sigma 1 logically implies, say, not P7 arrows P5. Why is that the case? Yes.
Well, for the truth assignment that makes sigma 1 satisfiable, i.e. everything is true.
Right.
Then that holds for that.
Right. So the only set truth assignment that I should consider is that one that makes all of them true. And if all of them are true, then this is false, this guy, and then this is true. Okay? And we have relationship between them. So here is a very simple claim that sigma when sigma consists of just one formula alpha, so say sigma is alpha, then sigma for all beta, for any beta, sigma logically implies beta if and only if alpha logically implies beta, which is basically the same definition. Because if I have a truth assignment that satisfies all members of sigma, it's a truth assignment that satisfies alpha, which means that sigma logically implies beta, means that alpha implies beta. Yes?
Does that notation for logically implies only apply for sets implying?
Okay, so that's a good point. We will also use this notation. So here is just a comment about notation. We will therefore use the same notation for logical implication between formulas. So we will write alpha logically implies beta in the same way. So one interesting conclusion is that so here is a very simple just corollary of those definitions. If sigma contains a contradiction then for every formula alpha, sigma logically implies alpha. And again, if sigma, what does it mean sigma logically implies alpha? That every assignment that makes everybody in sigma happy will make alpha happy. But since it contains a contradiction, there is no such assignment. So this holds vacuously. Yes?
So it's if sigma contains only a contradiction?
No, I assume that sigma could be something very big. So say sigma has P1, P2, P3, P1 arrows, P3, P5, and not P1. Oh, say P1 and not P1. So here is my sigma. So it contains a contradiction. Right? Now I say it logically implies every beta. Because logically implies means that whenever I can find a V that makes all of them true, this V should also make beta true. But I cannot make all of them true. I mean, that's a good point, because you have to notice that the notion of sigma logically implies alpha only talks about assignments that make each and every member of sigma true. It doesn't talk about assignments that make some of them true and some of them false. Yes?
Can I ask what's the difference between choose assignment that makes sigma true and the P1, let's say, using and makes all of the formulas inside sigma?
What are you saying?
Okay, as an example, let's say sigma contains formula P1 to Pn,
Okay.
and then start the same with P1 and P2 all the way to Pn.
And. Right. So I can translate your question into a claim. So this is a claim that if sigma is a finite set of formulas, namely sigma is some alpha 1 ... alpha n, it's only finitely, then for every beta, sigma logically implies beta if and only if the formula alpha 1 and alpha 2 and alpha n logically implies beta. I'm missing a lot of brackets here. But this is a single formula. This is single formula, and this is a set of formulas. And this set of formulas logically implies beta, if and only if this single formula logically implies beta. And just prove it on your own as an exercise. The truth of this statement relies on the truth table of end. But if sigma is infinite, I cannot do this trick. Because if I make an end of infinitely many formulas, it's no longer a formula. So let me just tell you one anecdote about this notion. The philosopher, mathematician that developed all of this theory in a formal way was Bertrand Russell. He was a British philosopher, the beginning of the 20th century, and he gave a talk about this to kind of general audience that is interested in science. And he said, if sigma contains a contradiction, then sigma implies every other statement. So, in other words, if you assume a contradiction, you can prove everything you want. So, assuming, if you assume a contradiction, then any statement follows. That's basically what it's saying. So someone in the crowd was not very happy about this statement. So he said, okay, are you sure this is the case? And Russell said, sure, I know my math. So he said, okay, so let us assume that 2 and 2 equals 5 and prove to me that I'm the Pope. I mean, 2 and 2 is 5 is false. So you should be able to prove anything. Oh, so prove to me that I'm the Pope. So, what?
Either 2 plus 2 equals 5 or you're the Pope. And clearly 2 plus 2
Why is it the case?
Well, we know that 2 plus 2 equals 5, right? So 2 plus 2 equals 5 or you're the Pope is a true statement, right? Because 2 plus 2 equals 5 is true. Now, given that we know that, we know that 2 plus 2 equals 5 is false.
You're kind of...
Therefore, you're the Pope. And the or means you're the other side, so you're the Pope.
You're kind of cheating, telling me at the same time that it's true and it's false.
Yeah,
but,
I need a real contradiction rather than just a false statement there. That's why I need a contradiction.
But what Russell did is he just stretched it a little bit longer. He said to the audience, okay, I'm not, he said, okay, let us assume 2 and 2 equal 5. We also know that 2 plus 2 equals 4. Now, by the transitivity of equal, now if A equals B and B equals C, then A equals C, we get that 4 equals 5. Oh, don't worry, we're on our way to the Pope. Now we said, if that's the case, then we could just do some math manipulations, then 4 minus 3 equals 5 minus 3. Because if those are equal, I subtract the same number, I'll get the same result. Okay, so I get that 1 equals 2. Now, you and the Pope are 2 people, but 2 is 1. So you are the same person. But you must admit that this proof is more entertaining than yours. Right?
Yes.
Okay. What? I don't know. The anecdote ends there. Right? Yeah. Okay, so we have this notion of logical implication and satisfiability for sets of formulas. And now there are lots of things that are completely non-trivial that follow from it. Some of them, let me just make 2 statements just to show you. Because, you see, until now, you remember that we started the course with saying, why do we need logic if we have common sense? If we made it into computer science in Waterloo, then we are smart enough that we can trust our common sense. And all of those games that we're playing so far were kind of this flavor. I mean, if I give you the definitions and you think about it for a minute, you can show me all my claims so far. So let me show you some claims which are not so obvious, and then so not obvious that I will not prove them now, but we will prove them in the continuation of the course. So 2 non-trivial statements about these notions. I mean, if you have just look for mathematical challenges, you can try to prove them yourselves, but it's completely far from being easy. So the first one is called the compactness theorem. And the compactness theorem says that for every set of formulas sigma is satisfiable if and only if every finite subset sigma prime subset of sigma is satisfiable. So if I give you an infinite set of formulas and ask you, is it satisfiable, it's enough to show that every finite piece is satisfiable. And we will prove it eventually, but it's completely non-trivial. Another one, so you see what if sigma is satisfiable, then it means I have an assignment that satisfies all the formulas in sigma. So in particular, this assignment will satisfy all the formulas in every sigma prime, which is a subset. But the other direction is not obvious. I have a finite subset, I can satisfy it. I have another finite subset, I can satisfy that. But I have to satisfy all of sigma simultaneously. So I have pieces. Each finite set I can satisfy, but how can I be sure that it's the same, that I can find one single assignment that will satisfy all of them simultaneously? The other one, which is also non-trivial, also I will not prove it now, I'm just giving you some challenges or showing you that those things can become interesting. So the other one is called Craig's interpolation theorem. And Craig's interpolation theorem says that if whenever let's show it for formulas. Whenever alpha logically implies beta, then there exists a formula gamma with such that we have two requirements. One, every propositional variable in gamma appears both in alpha and in beta. So you see, alpha and beta, maybe alpha has different variables and beta has different variables. But gamma should have only variables that appear in both of them. And two, alpha logically implies gamma, and gamma logically implies beta. So that's why it calls interpolation theorem. I can stick something in between that only talks about the variables which are common to both alpha and beta. Okay, so both of these statements are something that it's not an open question. It's not like, the question that I asked you before, the $1 million thing, find the algorithm that will decide satisfiability in time less than exponential, that's $1 million question. Unless we have a lot of self-confidence, I wouldn't spend my time trying to solve it right now. But those are, if you have free time, you cannot fall asleep at night, then you can think about it. Maybe you'll come to the answer, and eventually we'll show them. Yes?
Are both theorems true?
Yeah, both of them are true. Yeah, both of them are true. Both of them are theorems. That's when I say theorem, I usually mean some. Otherwise, I would call it conjecture or riddle or whatever. Yeah. Both of them are true, and we will show both of them eventually in the course. Okay, so let us move on. So the question that I want to address next is our choice of connectives. So we decided to have our propositional logic, our definition, semantic, or our definition of propositional logic was based on the connectives neg and or an error. And what I want to ask is, why this? Why not something different? So, how general does it make our logic? Could we have done better? So for that, I will say that, so what are connectives? Connectives, I mean, again, we are in the semantics realm now. So for us, connectives are identified with the truth tables. So we have 4 truth tables, and those 4 truth tables are the basis of our semantics. So could we build the logic on other truth tables? So let us say that we say that f, so we had a definition here, f, a truth functional, is a function f from Tf to the power n for some n to Tf. So each of our truth tables is a truth functional. Each of the 4 truth tables is a truth functional. Right? What is the n for this truth table? 1. And for the others, the n is 2. They go from pairs of truth values to 1 truth value. So each of them is a function, right, that goes from pairs of truth tables to, right? So we can think of it this way, that we have here this, if I have 2 values, I have here tt, tf, ft, ff, and a truth function maps them. So say, if I look at the truth function of and, it goes from these 4 vectors, 4 pairs, and it maps this guy to true, this guy to false, this guy to false, this guy to false. So I can think of and as a truth functional. It takes pairs of truth values and it outputs truth values. So there are truth functionals which are not one of those. Can you show me an example of a truth function which is not one of those? Yes?
NAND in verbal things?
Right, so I can say, what about the function NAND that is defined as follows? You take TT, TF, FT, FF, and you map this guy to false and all the others to true. So that's a truth functional that was not one of the 4 that we had there. And I can also talk about truth functionals for other n's. So for example, if I take n for another example, for every odd number n, let Maj n be the majority over Tf to the n. So what will be, for example, Maj 5 of the assignment T, T, F, F, F? So it's a functional that takes a vector of 5 truth values and gives me 1 truth value, which is the majority. Okay, so truth functionals do not necessarily have to be 2 places or 1 place. They could be many places. How big will be the table, the truth table of Maj 5? How many rows will I have in the truth table? The truth table will start with 1, 2, 3, 4, 5 t's. Then it will go to 1, 2, 3, 4 false, all the way to 1, 2, 3, 4, 5 f's, and I'll have 2 to the power 5 lines. I have 32 lines. So for each of them, there will be a value. The value here will be true, the value here will be true, the value here will be false. For each of them, there will be a value. So it's a function that takes 5 tuples and outputs 1 value. Okay? So we can see that our connectives, if we look at them from a semantic point of view, they're just truth functionals. They're just a few of the many, many truth functionals that one can come up with. So now we say so now we have an interesting definition. So we have a definition a set of truth functionals is called adequate Did I forget any letters here? More T's, more, that's it? What? That's okay? It looks strange, right? So what am I missing?
It's Q-A-T-E.
Okay, add the, what?
A-T-E.
80. Okay, yeah. I knew something was wrong. Okay, it's called adequate if a propositional formulas over that set can express every possible truth functional. So I want that the formulas that I built will be able to express every possible truth functional. So for example, can you give me a truth? Can you give me a formula? Find alpha in the connectives that we usually use that expresses Maj 3. Say over, you have A, B, C, that's your variables. How can we write a formula that will be equivalent to the majority over those three variables? Anybody has an idea? Yes.
A and B or A and C or B and C.
Right. So let's, for example, we can take alpha to be A and B, or A and C, or B and C, and add some brackets to make it complete. So this formula is true if and only if the majority of ABC is true. But, okay, so we can express majority over 3, and it's easy to see that we can actually express majority over any n. But now, is our set adequate? So here we have a theorem. I mean, it's expected. The set that we are using is adequate. And then we can also ask questions of are there other adequate systems? When does a set becomes inadequate? Can you show that something is inadequate? It gives me a lot of room for assignments and questions to torture you with. Okay, so let us prove this as the last thing that we'll do today. So the proof, so let f be any truth functional and consider the truth table describing f. So what does it mean? Say f is a formula with n variables. So I'll write here p1, p2, up to pn. And here I'll write f of p1 up to pn. And I'll have here all the possible values from true, true to everything false. So I'll have here a very big table, 2 to the n rows, and each of them will have a value here. Some of them will be true, some of them will be false, some of them will be true. We don't know how. And now I want to find a propositional formula that expresses exactly the same function, such that the truth table of this propositional formula will be exactly this table. So what are we going to do? So for every, so let us just introduce a few notions that are common in logic. So a literal is either a propositional variable or its negation. Not P. That's a literal. And a conjunction or let's call it a monomial, is a conjunction which means just and of literals. And okay, and this junction, okay. So I don't have a good name for this junction. What? Yeah, okay. We'll also consider this junction of monomials, of literals, is a formula of the form L1 or Lk, where each Li is a literal. Okay, so now what we are going to do is we are going to kind of describe this truth table. So for every row in the truth table, we will write a monomial. So for each row I in the truth table of F, let alpha I be the monomial which is L1 I up to end Lni. It's the ith row, and we have n literals, where L I j is equal pj if the j's variable. Okay, I'm running out of time. Oh. In the ith row gets value t and not pj otherwise. Okay, so this is really cumbersome way of describing it in words. Let me just show it by example. So the first monomial, my first alpha I, alpha 1 will be P1 and P2 and Pn. And the last one, alpha 2 to the n, will be not P1 and not P2 and not Pn. So each alpha I describes a row in the table. And then what we will do, so we have for every table, so alpha 2 will be P1 and P2 and Pn minus 1 and not Pn, and so on. I get one monomial for every row in the table. And then my alpha of f will be just the O for all I such that f of this alpha I is true of alpha I. F in the ith row. But we don't have time. So, okay, you can think about it, but I'll go over it again when we meet again on Thursday because we ran out of time. So I'll just describe every row by a monomial, and then I'll say O over all rows that compute to T. So I'll go over it again when we meet on Thursday.